And I'd like to thank organizers for inviting me to this very exciting meeting. So, okay. So last year, cryo-EM single particle analysis achieved true atomic resolutions reported by two different groups. They utilized apoferritin and determined that 1.22 angstrom resolution from Cambridge group and 1.15 angstrom from Max Planck group. And Cambridge group also determines GABAA receptor, a real-life membrane protein sample at 1.7 angstrom, which is very high resolution for single particle analysis. And they used REFMAC 5 to refine the structures, and some new developments were there. So today I'd like to talk about high resolution features in EM and some new developments in the refinement. So the most exciting feature is hydrogen density. In apoferritin's 1.22 angstrom map, we could see hydrogen of water molecules. And even at 1.7 angstrom resolution map for GABAA receptor, we observed some hydrogen density. An X-ray crystallographer may wonder why only 1.7 angstrom resolution enabled it. And you may also wonder why these density peaks are slightly off from the hydrogen position in the model. I'll try to explain these things first. So let's review the scattering theory. So X-rays are scattered by electron density, and the neutrons are scattered by nucleus. And electrons in cryo-EM single particle analysis or electron diffraction, electrons are scattered by the electrostatic potential, which is formed by both nucleus, positively charged nucleus, and negatively charged electron density. So the atomic scattering factor for electrons can be described by this Mott-Bethe formula, where Z is atomic number or nucleus charge, because nucleus is point scatterer and described by delta function, and minus Fx. Fx is a atomic scattering factor for X-rays. That is a Fourier transform of electron density. But here it was assumed that this electron density is centered at the nucleus position. But this is not actually the case for hydrogen. Hydrogen's electron is shifted towards the parent atom. So the situation looks like this. And we need a phase shift term in the formula. And how hydrogen's density in EM would look like can be simulated by the Fourier transform of this function. And here is the result of some calculations. And I'm comparing it with X-ray density for three different resolutions and for different atomic B values. Let's assume that there is a carbon at the origin, but I'm not showing carbon density. And at 0.98 angstrom, there is an electron density center of hydrogen, and plus 0.11, there is nucleus, the proton. So for X-ray cases, the density peak of hydrogens always the same for any resolution or any atomic B values. But in EM case, the hydrogen density peak is off from the electron density center and the nucleus position. And peak position changes depending on the resolution cutoff and the atomic B values. These numbers are density peak positions of hydrogens. This is very interesting feature, and this should explain why we see peaks off from the expected position of hydrogen. And here, I am showing the simulated benzene density for EM and X-ray at 1.22 and 1.7 angstrom resolution. In the top row is hydrogen only density, and the middle row is carbon only density, and the bottom row is complete benzene molecule. As you will see, hydrogen density is more prominent in EM than X-ray. And even at 1.7 angstrom, you can see the peak elongation due to the existence of hydrogen. Because density contrast between different elements is smaller in EM than X-ray, so we can easily see the light element, such as hydrogens in EM. So that's why we observed some hydrogen density at 1.7 angstrom resolution. So you may want to ask, what is the lowest resolution to see hydrogens in EM? I don't know the answer, but as long as I looked at some EMDB entries, in the F4-FC map, there was some very likely hydrogen density, even at 1.9 or 2.0 angstrom resolution. So you may have a chance to see hydrogen around 2 angstrom resolution, but in very well ordered region, but it should depend. And in REFMAC, we can use Mott-Bethe formula-based electron scattering calculation throughout the refinement. And for hydrogen atoms, the nucleus position is currently hard-coded, but the new monomer library, which will be released in the next update, will include the nucleus distances in the bond length section, so that any program can utilize this for neutron diffraction and X-ray diffraction and the electron microscopy. And I have shown, as I have shown in this talk, F4-FC difference map is very useful and essential to see very small features like hydrogens. But we need to use different formula from crystallography, because in crystallography, we do not have observed phases, and we need to use phases from the model, which have large errors compared to amplitudes. So we usually use weight based on the estimated accuracy of phase information. And the equation looks like this. But in single particle analysis, we do have observed phases, and the errors exist in the complex plane, and the amount of error can be estimated from the half maps. And we can use weight using this variance of noise and variance of unexplained signal, like crystallography. And one option to use to calculate F4-FC density is like this, can be like this. And the derivation can be found in Garib's 2016 paper. And this F4-FC difference map is useful not only for seeing hydrogen, but also the model rebuilding in real space. This is the left panel is 1.7 angstrom resolution example, and you will immediately see how to fix this phenylalanine side chain conformation. And in the right panel, even at 3.3 angstrom resolution, we can find the error in the model and fix the model using the F4-FC density like this. So next, I would like to talk about symmetry, treatment of symmetry. So single particle analysis structures very often have some symmetries. And if the symmetry is imposed in the map reconstruction, then the structure model must follow that symmetry, like crystallographic symmetry. So we only want to refine the asymmetric unit. In this case, we can utilize NCS constraint function in REFMAC. We give only the asymmetric unit model and the whole map. And the REFMAC 5 internally considers the symmetric copies. if you give NCS instructions, and the coordinates file with annotation of symmetry will be written. But some important features to use this function were missing, and they were newly implemented in REFMAC and will be released in the next update. They include non-bonded interaction between the symmetry copies and the ATP similarity restraints with the neighboring atoms in the symmetry copies. And symmetry expansion of anisotropic ATP was also needed for apoferritin refinement. And the treatment of special position was also needed to for atoms sitting on the symmetry axis to keep that coordinates on the special position, and the anisotropic ADP needs constraint to be consistent with symmetry of the axis. So in that way, we refined the structures and deposited the asymmetric unit model to the PDB. And I hope this deposition of asymmetric unit model will be a common practice. But in that case, we should very carefully review the model so that symmetry information was correctly annotated. And I'd say the deposition system needs upgrade because currently the symmetry information is not used in the contact analysis in the model validation. And user-supplied symmetry information is not validated based on the map file. And so our group is currently actively working on making tools to validate symmetry of the map. It includes a pro-shade written by Mikal for symmetry detection, and the EMUDA by Rangana for operator refinement and the decision making. These tools will play some role in the PDB deposition system, and will be also useful in the refinement pipeline. So in summary, hydrogen atoms can be visualized more easily in EM than X-rays, but hydrogen density peak interpretation is a bit complicated because it depends on nucleus position and electron density position and resolution and ADP. And the F4-FC difference map is very useful to see hydrogens and model errors. And if map is symmetrized, the structure should be refined as a symmetric model, and only asymmetric unit model should be deposited with careful annotation of symmetry. And as I have shown, half maps are very useful to estimate errors in the observation, so please deposit half maps as well. Finally, I would like to thank Takanori, Scholz, and Ria Radu for this great collaboration, and scientific computing group at LMB, and Garif and the group members. And thank you very much for your attention.